Yeah, so let us start. So let us welcome Arnav Jayswal, today's speaker. He is a second year student at the Chemical Engineering Department of IIT Bombay, and he is a part of the Krittika Astronomy Club at IIT Bombay. And today he is going to speak on Cepheid variable methods. So let us all welcome him and hope we have a wonderful session. So, Arnav, it is all yours.
Yes, thank you so much for the introduction, sir. So I'll start. Let me just start by sharing my screen. Uh, just a sec. Yeah, just a sec. No, wait. Sorry, shared the wrong screen. Mm, just a sec. Just give me a second. I just need to load the presentation. Yeah.
Yeah, one just question. So, you will be taking the questions in between or after a
Uh,
regular interval?
anyhow, I think in between is also fine. So can everybody see my screen?
Yeah. Okay.
Can you see my
Yeah.
screen? Yeah.
Yeah. Yeah.
Yeah. Yeah. So hello everyone, I'm Arnav Jayswal from IIT Bombay, sir introduced. So today we'll be looking at just various ways we measure distances in astronomy. It's called distance ladder. Let's start by understanding why we need to find out distances. Like the measurement of distances is the most fundamental and trivial thing which we take for granted in astronomy. Like we see scientists and everybody just throw out big terms like this galaxy is this many million light years away and this many thousand light years away, and we just take it for granted. But we really don't know how you do that because there's a lot of nuances which go into measuring that. The measurement of distance is the first step to understand so many astronomical properties like stars, nebulae, and like also physical constants like the Hubble constants. And after you have accurate distance measurements, you can also find out a lot of different properties about the body you were finding the distance to, like mass, luminosity, diameter, age. So in its essence, a complete study about astronomical systems can't be done without knowing how far away it is. So no, so knowing how far away something is one of the most fundamental parts of astronomy. So how do you do it is the question. Like just like if you want to measure your height, you would just take a meter scale and measure your height. But if you have to measure the distance from my house to Delhi, you can't just take a meter scale and go on measuring it. You'll have to use some different methods. You'll have to maybe like take a satellite image and so methods like that. So you can't just use a standard method to find out any distance in the universe. You need to have different methods for different distances, as we know in our day-to-day life too. So, also just a small PS here. Kritika, the Astronomy Club of IIT Bombay, has our summer programs called Kritika Summer Projects, where experts in astronomy, in computational astronomy, actually help you get real life experience. And the assignment for it is pretty challenging. It's open for everybody in India. And you know this part is crucial because this was a major part of the assignment last year. So yeah, that is why I've just added that small part. So yeah, let's move on to the next part. So let's start by the parallax method. I'm pretty sure some of you would be familiar with what the parallax method is, but let us just go over it quickly. So as you can see in the diagram, so basically over a period of 6 months from June to December, as the Earth revolves around the sun, we measure the angle subtended by the arc from the foreground from the star in a background of distant stars, and based on that you get an angle p, and based on the angle p and knowing the fact that distance between sun and earth is one astronomical unit which we know, it is just simple trigonometry which I don't think I'll need to elaborate on about how you can find a distance from earth to star. So it's a very simple and a very beautiful technique which we can use to find out distances of nearby objects. But as I said, parallax method is only useful if you want to find out distances of nearby objects, because as the distance increases between the objects, the angle subtended by the stars becomes too less for our devices aren't that sensitive to actually measure the distances that are that small and then find an accurate measurement of distance from that. So basically, we consider the range to be 100 parsecs for like very good accuracy. So till a distance of 100 parsecs you can find out the distance of an object using the parallax method. But after that, there's an obvious need for other methods. But but with slight inaccuracies, you can go till about 1,000 to 2,000 parsecs pretty easily. But if you want a pretty like really accurate estimates, you go till about 100 parsecs. So that's the parallax method to find out distance between any stars. It's basic math. I mean, even if you are dedicated enough, I'm pretty sure you can do it. So it's just like pure genius, but very simple. So that is basically parallax method. But well, parallax method doesn't work everywhere. So now we will go to Cepheid methods. So does anybody know what Cepheids are, or does anybody know what Cepheids are or Cepheid variables? Uh, okay, it's fine. I'll tell. So yeah. So basically, Cepheids are these type of special stars, and Cepheids are yeah, variable stars, as a lot of people said. Yeah, periodic change in brightness. Yeah. So Cepheids are these type of stars, like special type of stars which exist, and they have sorry, they have very variable brightness. And why that is because there's a ton of reasons. There's the hydrogen and helium, there's the opacity change and stuff. Let's not go into that. We can discuss that after the lecture if anybody's interested. But yeah, so basically Cepheids are stars with varying brightness, and they have a fixed time period in which the brightness varies. And the astronomers have like taken great use of this very basic property of these very special stars to find out distances between the stars. So basically, later on, I'll show Jupyter notebook, which uses data collection from Gaia and Hubble to confirm distance to different galaxies. We'll look at the code later. Let's understand some of the theory now. So yeah, so Cepheid variables, just to recap, are stars which have variable fluctuations in brightness. So yeah, so basically the Cepheid method is used to measure distances, or used to measure distances to galaxies or any other astronomical objects, like akin to a galaxy cluster. So basically, there's a distance modulus formula which we need to first go over. So the distance modulus formula says small m minus big M is equal to 5 log d minus 5, where small m is the apparent magnitude and big M is the absolute magnitude. What's the difference between the both, you may ask? The apparent magnitude is the magnitude, like the brightness magnitude of the star we perceive from Earth. Like sitting here, the brightness of that star is the apparent magnitude, and the absolute magnitude is like the actual magnitude of the star. Like because different stars are mass are like some stars are huge but they're really far away, and some stars are like a huge magnitude. Some stars are pretty dim but they're close, so they might appear at the same apparent magnitude, but they have a different absolute magnitude. So our final goal is to remove the distance, right? We have to measure the distance. And what can we measure from Earth? We can measure a couple things on from the Earth. We can obviously measure the apparent magnitude from Earth. We can measure the apparent magnitude from Earth, and we can also obviously see the time period of the fluctuations. So because there are brightness fluctuations in Cepheid variables, we can see that we can see the time fluctuations in Cepheid variables. Now the fact is, how can you use this seemingly random fact of time, like the time of the Cepheid variables, to calculate the absolute magnitude? So that is when just a sec. Yeah, that is when the period luminosity relationship comes. So a brilliant scientist called Henrietta developed and observed this formula. It basically says that the absolute magnitude of a star is is a linear combination of the log base 10 of its time period in days. This is this was basically a game changer because you can't actually go there and measure the absolute magnitude, right? But basically, she observed absolute magnitude of some stars which are close by. You can do that, right? So basically, if you just see a star which is under the 1,000 parsec radius, you can just find the absolute magnitude of that because the absolute magnitude will be just luminosity by 4 pi d square. I'm pretty sure you're aware of that formula. And based on that, and we know the d, so we can find the absolute magnitude based on that basic formula of stars which are nearby. And based on that, she observed a very fascinating relationship that the absolute magnitude of the star is just a linear equation in where the variable is the log base 10 of the time period of the pulsations. But so m is equal to alpha log p plus beta. But the question is, how do we calculate alpha and beta? This is where the Gaia data comes in. So Gaia is basically this telescope which was sent, and it has calculated a lot of important data, like it has calculated the parallax angle, it has calculated the apparent magnitude, and like a lot of important properties of stars. We'll look into that later. So yeah, this is how you find the absolute magnitude. This is called Henrietta Leavitt's formula, or Henrietta Leavitt's law. So this is how, yeah. So this is how, using the distance, an apparent random variable, we find out what the absolute magnitude is. So now we'll check out how we find alpha and beta a little. Yeah, what alpha and beta, I'll elaborate about that when we go to the code. Alpha and beta are just constants, which we'll have to figure out based on data. I'll elaborate on that when I show you the code which I've gotten. So yeah, this is alpha and beta. So yeah, again, Gaia's data which I mentioned, Gaia will provide the following data. It will give you the apparent magnitude, it will give you the parallax, and it will give you the time period. Time period of the variable. This is what Gaia gives us, and then it will give us Hubble's data. Hubble also gives us the following data, but Hubble gives us data for stars which are really far away, like for stars which you can't find out the distance using the parallax method. So Hubble will give the apparent magnitude and time period for that. So based on Gaia's data, we will find out alpha and beta for big M. I'll just recap. So based on Gaia's data, because Gaia provides data of stars which we can find out using the parallax method. So one, we use Gaia's data to find out what alpha and beta are, which I'll show you in the code. And once you figure out what alpha and beta are, we can find the big M of any star, basically any star, any Cepheid variable. So after you find big M, you just apply small m minus big M plus 5 is equal to 5 log D. And just by simple algebraic manipulations, you can get D. So this is what our process is. So let's just look at the code. It'll give us a better insight. Just a sec. Uh, can you see my code, sir?
No.
No. Oh, wait, I'll have to share the different tabs. Just a sec. Uh, yeah. Can you see it now?
Yes.
Yes.
Yes, right? You can see it, right?
Yes.
Yes.
Yeah. Okay. So let us just go over this code, with which we can actually visualize the real data. So the first is just importing all the necessary libraries, and then I've just used simple pandas commands to read the CSV file of Gaia. So basically, what we are doing is we are using Gaia's data to get a scatter plot of big M and log base 10p, because based on the scatter plot, we'll draft a best fitting line, and based on the best fitting line, we'll get an alpha and beta. So basically, I've just applied simple code here. I'll just explain the code quickly. Basically, Gaia data will give us the parallax, and so it just gives us the parallax. So we can just find out the distance using the parallax, and you can find the mean apparent magnitude using the Gaia data again and again. So then again, you use the time period and you find the basic calculate, and you can calculate the absolute magnitude using the formula m is equal to small m minus 5 log 10 5 log base 10d plus 5. So using that, you find the absolute magnitude, and you just plot all of these. So plot all of these. Obviously, it won't be a perfect straight line, but you can just use linear regression to find out the best fitting line. So based on this, you get the value of alpha as this and beta as this. So basically, what we have done is we are using the parallax method to get the distances of stars which are close to us. Distances as in the absolute magnitude of the stars which are close to us, and using that data, we are generalizing a line for any star. So just using that data, we are getting a best fit line with which you'll get one alpha and one beta. And using that alpha and beta, you will plot the alpha, you will plot a best fitting line and just generalize this line for basic. And after you have alpha and beta, you can find out the absolute magnitude of basically any star. So this is the use of Gaia's data. We took all of this information to find out distances to stars close by us. Now Hubble comes in. So basically you're getting Hubble's data from like what Hubble is measured. And so Hubble has data which has for like really distant galaxies and galaxy clusters, for which you can't apply the parallax method. But we just fitted a best fitting line based on Henrietta Leavitt's formula to figure out what alpha and beta are to get the absolute magnitude for any star. So so I'll just explain the code again. So you initialize the dictionary to store distances and list for all distances, a basic Python, and after that you iterate through every single Cepheid stars data to calculate distances. So basically you go to every single Cepheid stars data. Then after that, you find out what the absolute magnitude is based on the relationship which we have obtained. And Hubble has provided us with the log base 10 of all the different Cepheid variables. So using this best fitting line, you find out big M. And after that, you apply the formula for distance, which is just a manipulation of this formula. Yeah, which is just a manipulation of this formula right here. D is equal to 10 raised to small m minus big M plus 5 by 5. So after that, you just manipulate the array to add all the distances of the Cepheids, and but you can't just publish this data. We also need to make sure that some errors are accounted for. So basically, obviously, there's going to be some human errors, and also there's going to be some errors from the equipment. So sometimes, so we call these errors outliers. So basically, in this code, the method I use to identify outliers is like if the galaxy distance is greater than is like if the galaxy distance is lesser than like if the galaxy distance is lesser than 2 into 10 raised to 7 parsecs or less or like greater than 2 into 10 raised to 7 parsecs or lesser than about like 100,000 parsecs, I've considered it as an outlier. This can change based on your code or what you consider or how much accuracy you want. So basically, if this condition is not satisfied, I have removed it from the data set. So after that, I've just plotted a histogram of galaxy distances, which we have seen here. And also, based on the outlier code I got, we noticed that one galaxy had distance of just 2383 parsecs, which is unfeasible physically. So you can't say anything about this galaxy's distance. So yeah, basically you use the data from the Gaia telescope to plot a best fitting line. Then you use that best fitting line to calculate the absolute magnitude of the galaxies which are far away. And based on that, you just use our simple distance formula to find out the histogram of galaxy data. So this is what we have done. Does anybody have any doubts? This was pretty
In
heavy.
this case, when you're talking about galaxy distances,
Yeah.
basically you're taking Hubble data uh, where Hubble has measured a variable star from particular
Yes.
galaxy.
Yes.
Okay.
Yeah. We are measuring the distance of variable stars, but yeah, we are just considering them as star clusters. Yeah. Any other doubts? I'm pretty sure this was a lot to digest. Okay, I guess we can look after it later. So let's go back to the presentation. I have some more very interesting stuff to share. So yeah, file, just a slideshow. Yeah. So we basically saw Hubble's data, we saw Gaia's data, and that this is a Cepheid variable method to find out distances of uh, Cepheid stars. And once you know the distance of a Cepheid star, you can find out the distance of the stars nearby to it using parallax method. So you can find out. Wait, there's some doubts. Yeah, the outlier criteria I chose was subjective. You can discuss it. You can use pulsars instead of Cepheids too. You can use pulsars. I think you can. I'm not very sure. Type 1A supernova you definitely can use. Pulsars, I'm not sure if you can use them. So I'm not
The
really sure
pulsar
about that.
won't have this kind of time luminosity relation.
Yeah, pulsars. Yeah, this specifically was Cepheid variables just because of the mechanism in which they work. Yeah, you're right. So yeah, so this is about Hubble's data. So I guess I'll move on. We can look after some other doubts after the section. So let's move on to something really interesting. So this was Cepheid variables. So are there any other methods except light through which we can measure distances to astronomical object? When we visualize about measuring distances to objects, we always think about okay, we always have to we always picture seeing the object and then finding out the data of that object through a very visual way. But there are ways by which you can measure a distance to an object without actually, getting visual data of that object. So this is something very interesting which I'll cover now. So this is called as a distance siren. Basically, I'm pretty sure all of you know what gravitational waves are. Basically, like Einstein's theory of relativity proven. So, like binary black holes, when they just rotate over each other, they produce ripples through the fabric of space-time, and these are known as gravitational waves. We detected a lot pretty recently. LIGO is an observatory which is working towards detecting gravitational waves. So yeah, so basically, the energy emitted through the gravitational waves comes directly from the orbital energy of the binary system. And the decrease in orbital energy corresponds straight to the increase in frequency. So basically, there's all these properties of gravitational waves. So, you can just picture it like the gravitational waves will be like the black holes will be like moving slowly around each other. And as they get closer, because of conservation of moment of yeah, the black holes will just go on increasing, and the frequency of the gravitational waves will increase. So based on this, scientists derived this formula for the frequency of gravitational wave. Df by dt is this huge expression. Let's not go into it. The derivation is not at all necessary for it. It's huge. But just consider this. So df by dt, where frequency is this differential equation, where the m is called a chirp mass. The chirp mass represents a quantity which is a combination of two masses, m1 and m2. m1 m2 raised to 3 by 5 divided by m1 plus m2 raised to 1 by 5. This is a chirp mass. Uh, so basically, our detectors, which will measure the gravitational waves, will measure the following things. They will measure the df by dt, they will measure the frequency, and they will also measure one more thing, which is the strain h, which is the strain amplitude. So basically, the strain amplitude is the strength of the gravitational wave. So basically, our detector will measure the df by dt and f, and from this differential equation, we will get the chirp mass. And after you get the chirp mass of this gravitational system, you can figure out what the strain h is. And the strain h is dependent on gm by c square into v by c, which is just frequency, gm by c square into f square into 1 by d, where d is the distance. Based on these two equations, from the first one we find the chirp mass, and from the second one we find a distance. So based on these two equations, we can find out the distance of from our planet to the binary black hole system or anything. So yeah, this is the strain. This is how these detectors work. So just to summarize, the detector will measure the strength of the black hole, the frequency of the gravitational waves, and also df by dt. And based on f and df by dt, you remove you find out the chirp mass, and based on the chirp mass, you can use the formula that the strain amplitude is proportional to g into this chirp mass by c square into 1 by d into frequency square. V by c is just frequency. But the thing is, this is a very ingenious method, but there's a couple of problems with this method. So the problems, I guess, are that gravitational lensing. So let me just go over what gravitational lensing is. You can picture gravitational lensing to be very similar to what the work an actual lens does. So just look at this diagram. So yeah, so light travels out from a quasar, and basically supermassive objects in the path of the light act as a lens. They focus the electromagnetic waves emitted from the object which we want to observe. They focus it and send it to earth. As you can see, the light travels out from the quasar. The galaxy's gravity acts like a lens, uh, as it as it diverges, and then it reaches earth. And based on earth, because of like the all the varying light rays, you perceive it as you have gotten like basically four different waves. So you don't so like basically gravitational lensing because of gravitational lensing, you can see like four objects which are surrounding the galaxy, which is explained by gravitational lensing. So basically, the method for this method is not a very strong method just because of gravitational waves. So gravitational lensing, if the gravitational lensing is strong, it may be perceived that multiple events are produced, just how we saw for the quasar example. If the gravitational lensing is strong, it might be result in multiple events. It might result in us perceiving multiple events at a time. And if the gravitational lensing is weak, so if the lensing is weak and the path is affected by many so weak lensing means like the path is just affected by many magnification demagnification events. Like it's not one single very strong lensing, but basically every single gravitational lens will just change the amplitude a little of the waves, or frequency of the waves a little. So based on that, weak lensing will affect the magnification and demagnification of the gravitational waves, because of which we will have trouble finding out the distance based on the formulae we saw that. The one interesting thing to notice is that if the binary system contains of neutron stars, the merger would be accompanied by kilonova or supernova explosions, which allows the distance to be calculated more accurately, measured by EM telescopes. So I guess, sir, I had given you a question to put on the poll about this concept.
Yes, I'll just put the poll. Yeah.
Yeah, because I'm like, this will be a yeah. So I just want to see like if people will think of why.
Yeah. The
Yeah.
poll is even.
Yeah. This was not the yeah. Sure.
It's the same poll, right?
That is 5. Yeah. We'll wait for some time for everybody to answer.
Yes, the poll will be on for another 2 minutes.
Yeah, no
Okay.
issues at all.
We can go more than that, but 2 minutes at least.
Yeah, no issues, sir. Answer key is also in there, right?
Yes, yes. So
Yeah.
we'll share the result after the poll is over.
Yeah, sure. Rakesh, I'm just reading your question. I just noticed it now. Yeah, as far as I know, yeah, the chirp mass is calculated with the peak strain measured in all of the papers. Yeah, you calculated at the peak from what I have read. Yeah, and I'm not sure about the first question. If the n number of neutrons once they collide, will the number of neutrons be conserved? I'm not really sure about this. I have not thought about this. I'm sorry. I'm not sure about this. But yeah, I'm pretty sure about the second part.
Okay, 1 more minute for the poll, then we'll end the
Yes.
poll. Okay, uh,
Yeah.
we shall end the poll now in 10 seconds. Okay, so I'll share the
Yes.
results here.
Yes. I'll do show correct answers to all too. Yeah. So
I
yeah.
think correct answers are shown here. Just check about the last one.
Yeah, I guess a lot of people got the uh it was a little tricky, I guess. A lot of people answered incorrectly. Otherwise, just a second. Does anybody have any doubts in the questions? Let me just. I think we don't really. Oh, we don't. It doesn't really matter. if we use type 1 or type 2, because all the Cepheids will have like the same properties. Yeah, okay, so let's
Yeah,
explain question
I
3.
think it was about supernova,
Okay.
and the type 1 supernova will be used because I mean all type 1 supernovas are ultimately when you cross the Chandrasekhar limit. So effectively the same
Yeah.
mass and therefore same luminosity. But type 2 supernova won't have that kind of limits.
I think he asked about type 1 and type 2 Cepheids.
Okay.
Yeah. Okay.
So in
So
that
I'll
case,
just
yeah.
explain question 3. So
Okay,
yeah,
okay.
why is the
Cephids. Yeah.
PL relationship specific to only Cepheid variables? And the answer is yeah. So basically, uh, I had just mentioned very briefly in the first point, but yeah, it really boils down to how seafood variables work, how seafood stars work. So seafeeds, so basically on the just outsides of the seafeeds, there's a hydrogen and helium, H plus and He plus ions, which are on the outside of the seafeeds, and basically there's radiation which builds up inside the star, which as it does in everywhere, and the outer layer is cooler compared to the inner layers of the star. So the outer layer react differently to pressure and stuff. So as the radiation builds up, the helium and hydrogen start He plus and H plus, they start combining, and the star starts expanding, till a specific opacity, and the star expands till the point where the radiation pressure where the till a point where the radiation pressure reduces, after which the star just goes back again. So basically it comes down to how Cepheids work. So that is why the answer was just was A. Yeah, the Cepheid variables pulsate due to unique resonances in the helium layers, which tightly linking the period and luminosity. Uh, so then the fourth question somebody asked, why do neutron star mergers produce EM signals? So yeah, this was also just a question I added for fun. I just wanted to see if everybody would know, if somebody could guess the last part. So yeah, so basically neutron stars are different from black holes, because black holes, they just produce ripples in space-time. But neutron stars, they actually eject material during the merger. So like when they eject material, they do release electromagnetic radiation too, and you can detect these electromagnetic radiations, and you can verify the results just based on this electromagnetic radiation. So as I've mentioned in the slides, uh, yeah, the explosion by kilonova or supernova by merger of neutron stars can be verified. Like you can obviously use the gravitational wave method, but you can also then yeah, they also eject strange fog, and you can also and yeah, so you can also verify the verify the distance by EM telescopes, and you can also verify the methods by like distances. So yeah, how does weak gravitational lensing affect distance measurements using gravitational waves? So yeah, just the last slide I had explained. So basically, weak gravitational lenses are not the weak gravitational lensing is not like strong enough for us to actually notice different different objects like notice this phenomena which I have shown in the slide. Basically, the strength is not strong enough for us to actually observe different objects at different time periods, or different waves, different time periods. But weak gravitational lensing changes the amplitude and frequency of the waves, which can cause problems in our measurements. So yeah, that is about question 235. Does anybody have any other doubts? Just a sec. Yeah. So we are basically done with the presentation. Does anybody have any doubts in the code which I showed, or just any concepts? I'll try my best to answer. I might have missed some questions, so just let me know.
If you can talk about from where to get the data and work on that, that will be
Okay.
useful. So the data
I
sources.
just took the data from the GEA website. I mean, I will share it with you for if you want it.
Eh, no,
You can just
if you can, because it is also being recorded,
Yeah.
if you can just go to the website and show how to search, if that is possible.
Just a sec actually, because my friend had gathered this. Like the CSV file was pre-made actually, so I'm not sure how I got it. But
Oh, that
I'll
is fine.
just
Yeah.
yeah. So I'm not sure, but I can ask somebody, and I can just definitely update you with it.
Yeah, and
Yeah.
we request you if you can send some of the CSV files on the Google
Yes,
Classroom
I
so
will
that
definitely send. No, the assignment
participants
which I
can
am thinking of
practice.
making for this is also based on the CSV, some CSV files which we will provide for you. So don't worry. And yeah,
Yeah, sure.
anything I can. So I'll share the code, I'll share the slides, and I'll share the CSV files. Yes, I'll share the four of the things. Yes. I don't think the V gravitational lensing doesn't. Wait, there's some questions coming. Yeah, the V gravitational lensing, uh, I don't. It doesn't result in a change of energy because if I'm where does this? Yeah, I'm not sure where does the energy go, but I'm not really sure. Let me think about this. No, see, we are not for Raj's question, the speed of the EM wave is high, obviously. It is traveling the ripple of space-time. But gravity of large objects is huge because you are like actually considering lensing by literal star galaxy clusters. So, and it's just not one single black hole. Like the entire galaxies or the entire cluster's gravity affects the entire electromagnetic wave which we are measuring. So yeah, it is not as small. It's not a very small distance. It's not a very small gravity. That's a wrong misconception. Yeah, it's a huge object by which it measures. Yeah, as Kavya said, it follows the curvature of space-time. That's why it bends. Yeah, so that is how you get it. Yeah. It's just not a single black hole. That won't be enough. It'll cause some difference, but it won't be very significant. But an entire galaxy can cause some pretty significant difference in the star. Yeah. So like, if there's any other questions, we can answer them. Or with this, that's all. That's it from my side. And yeah, I'll share the data in some time, as I mentioned, sir. I'll upload it on the Google Classroom, right?
Yes, upload it on the Google Classroom. If you are sending it as a practice data, upload it as material. If you are sending it as an assignment, upload it as assignment.
I'll upload the assignment later.
Yeah, okay.
Yeah.
So this you can send it as the material
Yeah, we'll
so
get
they
the
can
app and the
practice.
files too. Wait, just a second. I'm getting a phone call. Just a second. Excuse me. Uh, this is more. Somebody asked for somebody asked for the stellar evolution of Cephids, so I'll just go with that. Yeah, so basically, Cephids are usually evolved from stars with initial mass about, I guess, 5 to 10 times the solar mass. And yeah, they basically go through their main sequence like regular stars. They burn through the hydrogen core, and after that, obviously, you know how stars work, like hydrogen, helium, and वो सब होता है. So like they burn through the hydrogen cores, and after which they turn into red giants. And so the red giants are formed after hydrogen exhaustion the and the helium. And so after the red giant forms, I think the helium core is also starts burning after which just a sec, let me recollect. Yeah, basically after the hydrogen is burned through, the you start burning through the helium. And when you start burning through the helium, The stars will cross the instability strip on the HR diagram. And once they cross the instability strip on HR diagram, you will get the relationship which I mentioned before, where the opacity mechanism or kappa mechanism, which we call it, where the helium layers will drive the pulsation. So yeah, so I guess that's about it. I am about what you need to know about Cepheids. Basically, the stars are obviously larger than the hair. So yeah. So there, I'm getting a couple DMs if I could know about the summer school talk by the Krittika team. So if you want to know about that, I guess you can follow our Instagram. We will release it next summer. So you can check it out. You can check our Instagram page, kritika.iitb, and you can just see the previous year assignments and something. Yeah. Otherwise, I'm on the WhatsApp group. You can DM me. I can also just give you my number. I'll just put it. I'll just give you my number. And my email ID. If you have any doubts about anything, just mail me there. Yeah, I have put my phone number and email ID on chat. So if you have any doubts, you can mail me or contact me on WhatsApp about just details of Kritika and anything which we do, or just, yeah. So, yeah. Oh, the quick revision of the coding part. Sure, I can do that. Yeah, just a sec. I'll go to the, yeah. Can everybody see the screen?
Can you
So
slightly zoom in?
I'm not able to on this. I'm sorry. I'm not able to zoom in. It's not visible.
No, it is visible. It is just that
I don't worry. I'll share the Jupyter notebook later. Uh, yeah, I'll share the Jupyter notebook later. I'll just run through the main concepts. I'll share the Jupyter notebook ASAP.
Font size setting is under view section.
Oh wait, I have not played around with it. Okay, just a sec. Appearance. हाँ किधर है appearance?
Under appearance, you can see zoom in.
Wait, just a sec. Yeah, zoom in. Yeah, sure. This is better. Yeah, this is better.
Yeah.
Thank
yes.
you.
Yeah, so let's just run over the code fast. So basically, the Gaia data, which I'll share, the CSV file, we ran through the CSV file. The pandas read the CSV file. So yeah, the Gaia data, as we mentioned, will provide us with the parallax angle, the apparent magnitude, and the time period of the Cepheid variables. And you can use the parallax method because these are Cepheid variables which are in around 2 to 3,000 parsec radius around Earth. So you can use the parallax angle to
Yeah,
find
just can you show the info of the CSV file, that data frame you have?
it's it's on my, just a sec. I'll just
I
a
mean,
sec.
if you just run it here,
Yeah, just a sec. Uh,
just to check the fields, because what are the fields available? So
yeah, I'll just upload it. Yeah, just a sec. Fine. Open. Yeah, Gaia.csv. Yeah, can you see it? Yeah.
yes.
Yeah, time period, apparent magnitude. Yeah. So these
Yeah,
are
so
the, yeah.
four fields, 5 fields are there.
Yeah.
Four fields,
Source,
sorry.
yeah. Mean, yeah, 4 fields. Source ID, mean apparent magnitude, time period, and parallax. Yeah, as we said. The apparent magnitude is what we need. The mean apparent magnitude, obviously, because the magnitude is changing for the Cepheid variables. So you take the mean apparent magnitude, the time period and distance of the pulsation, and the parallax angle, which I've mentioned in the book. So yeah. So we started by is everybody familiar with like linear regression and how you can apply it on Python? If not, you can just check it here and you can just chat GPT it, to be honest. It's pretty trivial. It's not a very difficult thing to do. So yeah, you basically take the data given by Gaia, and based on the parallax, you remove the distance of these stars which are nearby to us, and and you plot this against the log of p, which is also given by Gaia. So you plot the absolute magnitude with the log of p, and for the stars which are near to us, and based on that, you form the best fitting line. So based on the best fitting line for the stars near to us, you get an alpha and beta. You get an alpha and beta, which is this, and after you get the alpha and beta, you just expand it to the Hubble data. So for the Hubble data, you read to the cepheid.csv file. The cepheid.csv will have the just one less column. It won't have the parallax angle. It will just have the mean apparent magnitude, and it will have the it will have the mean apparent magnitude. And just a sec. And it'll have the time period, obviously. And it'll have mean apparent magnitude and time period. So using the data in the Hubble's file, you use the same formula, the manipulated distance formula to find the distance, and you find that distance using to find a distance you need the big M. And how you find the big M? You find the big M by using the same line you fit in this using the same line you fit for the stars which are near to us. You find the big M, and then you can generalize the real magnitude for any star based on this formula which we have arrived at using Henrietta-Leavitt's relationship. And so yeah, based on that, you find out the distance, but you can't just find out distance anyhow. So you also have to check for outliers, which I mentioned is again a subjective thing based on how much accuracy you want on your code. So for this, for what I have done, it is distances less than 100,000 parsecs and greater than 2 into 10 raised to 7 parsecs. So I have removed all galaxies and all Cepheid variables which are greater than that, and I've just assumed the distances are just that off, just because it's an error. Yeah, I'm sorry. I'm sorry.
No, I think
No,
you
there
carry on.
was a
Somebody's mic was on.
I'm sorry. Yeah, I'll just go back. Yeah. Yeah. So as I was saying, yeah. So the method to find out the outliers is again dependent on how much accuracy you want. So based on the method you to find outliers, you remove the outliers, I've just found one outlier with this ID. You can play around with your methods to find outliers. You can figure it out. There are a lot more detailed methods to find out outliers, but I have used a really simple one for this code. I can share some of the detailed methods with you later on if you want. I don't have the code for that now, but I can definitely share that with you. It's a lot more involved, but I can share that. So yeah. And so you
how
remove the
about
outliers.
how much is the change in variance that you get?
It's quite a lot actually. Like this is my code. I didn't really take that many efforts, but I had a friend do a similar code, and he almost got 200 outliers out in the galaxies. And yeah, he had a different metric. I'll definitely get that code. So
No, but
there is a huge
what
difference.
is typical sigma value or the variance that you see with
Yeah,
after removing outliers? Because if you look at the scatter plot, it shows a lot of really lot of thick scatter plot. The
yeah,
first plot that you had shown.
yeah, yeah. This one, right?
So, yeah. So what is the kind of variance that typically you get?
Uh, for outliers, from what I have experienced, it's about 100 to 200. So a variance of, I'd say, yeah, 30,
And
40.
if you have calculated that, just show that code. That's it. I'm
I have
just
not
asking.
calculated it. Yeah, I'm
Okay,
sorry.
okay, fine.
I'll,
Yeah,
I can definitely share it later though. If you, yeah.
sure, sure.
Yeah, so I guess that is revision of the code. So yeah. So So, anything else which you guys want to ask? If there's nothing, so I guess we can end the session. I'll share the material.
Okay. Any questions? You can please unmute and ask. Otherwise,
Yeah.
we'll end the session. So let me take this opportunity to thank Arnav mm, uh, for the wonderful lecture. He's taken us through the different methods of using Gaia and Hubble's data and using different filters. Okay, we can calculate uh, some of the parameters which would be helpful uh, for the further sessions. Thank you, Arnav, for the
Thank you so
wonderful.
much. It was a pleasure.
Yeah,
Yes. Yeah.
thank you.
Thank you so much. Happy New
Mahesh,
Year to everyone.
Happy New Year to everyone. So, Mahesh, next session.
Yes.
And
Yeah. Thank you and happy New Year to everyone. Next session we will begin at 2:30.
I can leave, sir, right?
yeah,
Yes.